Thank you very much for the kind introduction. I'm very sorry for this rather complicated title. My name is Enrico, and I'm from Ghent University. We're working around Biomimetic. And to explain this title, just need three concepts: nucleic acids, light, and proximity, because this is pretty much what we know now. So back in 2011, Macromolecular had the idea of using this small molecule, this current, to incorporate it inside nucleic acid strand and to target complementary single strand in the DNA. So what happens is that when we oxidize the furan, it generates this ketone molecule, which is a very powerful electrophile. And in presence of amino group, so the nucleobase of the DNA, this can react and lead to the formation of a cross-link. We started then to explore this through other approaches, like, for instance, peptide interaction and protein interactions. And then more recently, when I joined the group, I started to become very much interested in these secondary structures of DNA, such as I-motif and G12 So the first thing we started to do was to target them, of course, because they are pretty important. Why they are so important? So rather than double-stranded DNA structure that you're all familiar with, DNA G12 and I-motif can be also formed under particular circumstances. So G12 are formed by the stacking of this structure, which is called G-tetra, that is formed by four windings that they form a kind of oxygen network between each other, and they stack on top of each other from the secondary structure of the G12. For the I-motif, it's a bit more particular. You need acidic conditions in theory. And when you reach these acidic conditions, you have the hemiprotonation of the cytosine, and the intercalation of these motif goes to form the I-motif. So these structures are very important because of their localization, which is rather strategic, because they are found in the promoter region of many important proto-oncogenes and also in telomeric regions. So there is a big interest in targeting them. The point is that we are interested in targeting them in a way that is as specific as possible. So what we did was simply taking this G12 as a model system. We took the flanking region of the G12 and then we used peptide nucleic acid complementary to this flanking region. We equipped these G12 these PNAs with ligand that contains, of course, our furan molecule, and we tested the alkylation towards the G12 in presence of competing. So what we use, of course, non-containing ligands, furan PNAs to have an additional control. And this allowed us to be very specific and to target with very high specificity the sequence of interest, even in cell lines in presence of competing quantities of non-target DNA. But G12 are not only important for their therapeutic, well, from a therapeutic point of view as a target only, but as we saw in many talks, some altamers and some decoys can also form G12 and they can be used as such as therapeutic molecules. There's a very big problem with these altamers because of G12, which is in fact that unfortunately G12 are transient, meaning that they can assign different possible topologies, and some of them they are in equilibrium. The point is that only one of them most likely goes to recognize the protein of interest, the target protein. So to solve this issue, we decided to use again photochemistry. And we use a TBA as a very simple model system because there is a huge amount of crystal structure that allowed us for the rational design of this concept. So we took the TBA, we extended two bases. We added a reaction partner on one side and a reactive molecule on the other side, another base. And this allowed us to anneal the system so that these two molecules, they basically enter in touch with each other. And then when we're sure about the conformation, we shine light, visible light, UV light, depending on the chemistry we use, and we staple the structure. Our idea is to lock the conformation and maybe improve also the pharmacokinetics of these optimizers. So we use our fluorochemistry and we also benchmark it with another which is signed in carbazole that is used as a photochemical linker, is also commercially available. And these reacts with the time in the secretization reaction in presence of UV lights. Another thing we tested is an external photocross linker, which is a ceramic moiety that intercalates in polyethylene trails on the two sides and react, bridging two times which are adjacent with each other. So we use the beginning HPLC. We also did a lot of field experiments and CMS experiments, but I want just to show you how we followed the reaction in the most easy possible. That also allowed us to calculate the yields of reaction and to purify the products we want to isolate. So we have in both the cases of our furan in the sign of carbazole, starting material here, and then when we shine light, a new peak is formed. The peak is isolated and corresponding to the stapled DNA. This is very interesting because in the case of both furan and sign of carbazole, this kind of proximity effect allowed us to have basically peak-to-peak conversion, which is very nice. In the case of the photocross linker, the things were not as nice. We never managed to completely consume the starting material, and the overall yield was only about 60%. Nevertheless, we managed to have enough material to do a lot of experiments. We started with melting experiments at the beginning, and we monitored the thermal stability and what happens after the stapling of these structures. In the case of both furan and cyanovinyl carbazole, the stapling increased the thermal stability of the structure. And in the case of the xanthotoxin, in the toxic solar photocross linker, we have even a destabilization of the secondary structure. So the reason why we have stabilization in these two cases is most likely because of the external aromatic system that we add, which will increase the stacking interaction and stabilize the G-quadruplex structure. We also came up with another experiment which allows us to follow the topological stability of our molecule, which is basically adding cobalt or another disruptor or of the quadruplex structure that can be easily monitored by CB spectroscopy. So we titrate our solution, we follow the CB, and we see that the characteristic peaks of the G-quadruplex would diminish over the addition. Very interestingly, in the case of the PPA as such, after less than one equivalent, the system was completely gone. In the case of all the stable structure, there was some sort of resistance towards the unfolding of our apnea. In the case of both furan and cyanovinyl carbazole, around 3.54 equivalents were not even enough to completely unfold the stable structure. We also tested another experience with a molecular small molecule which is reported to induce some sort of conformational engine the structure. We discovered that the 168 small molecules actually able to produce either a parallel, unlikely G-quadruplex or multimetic parallel G-quadruplex from PDA. And this, what you can see here, the characteristic maximum of the antiparallel structure of the G-quadruplex completely diminishes, and then it forms this 260 nanometer maximum, which is typical of parallel G-quadruplexes instead. But mostly, the very interesting thing is that this is stable. Even out of the additional 10 equivalents of our ligand, we don't have any change on the conformation of our atom. We also did a bit of experiments with the NMR. So we synthesized a huge amount of our stable construct and we see what is going on the NMR to check if the reaction is really occurring and if the conformation is similar to the original PPA. Luckily, we have only an extra cytosine, so we can actually see at the NMR where the cytosine is. We react and we see the characteristic peaks of this cytosine completely disappear and forming these other two species, which correspond, of course, to the formation of the product that is desired. We can easily relate to that. We also performed some molecular dynamics inventions, and thanks to that, we could visualize some external interactions. First of all, the stacking interaction, which influence, of course, the stability by adding an extra binder on top of the tetra. and also the flexibility of the sample, which is quite important. Too much flexibility, too little flexibility is not good for making the system breathe. And this explains the effect on the cyanogen participant, which is not as stable as the fuel unstable. We also perform a series of biological and biochemical assays. Serum stability was the first one that we tested. So the natural TBA and also the unstable TBA with just a quantification, but not cross-linked, after about 2 hours, they are completely gone from the plasma. In our case, our modified stable constant stays for way more than 24 hours. By accident, I left the sample on the bench, injected it. I also added more serum to check if it was degraded. It was there after 1 week, it was still perfectly there. We also tested, of course, the binding of these concepts and the binding towards thrombin, of course, and all our concepts were inactive. So we still bind perfectly their original target. And finally, we took off our bloods. We went to the hospital and we asked if they can do the test with our own blood. And we showed that the proton time of our staple analog is visually the same as the original TBA option. We also expanded these methodology towards other aptamers. This one is very interesting. I wanted to show you very quickly. It's basically an essentially potassium lead switch. So we have lead. This structure forms an antiparallel equaliplex. We have potassium, and really this thing switches back into a parallel equaliplex. Our hypothesis is that if this staple occurs, this attestation wouldn't be possible anymore. And indeed, what we saw in CD spectroscopy is that after the cross-linking, so the formation of the staple, this transition was not possible anymore. So basically, after the addition of the salt, the bands remain exactly the same. Finally, we decided to expand the methodology also towards emotive structures. The thing of the emotive is that they are stable in acidic conditions, but if we increase the pH, they tend to not be folded anymore because of the lack of the cytosine-based parallel. And indeed, when we performed the pH titration, we discovered that there is some sort of stabilization of around 0.6 unit of pH towards more basic condition. And around, I think 25% we calculated of aptamers still folded under physiological conditions, which is an improvement considering the fact that they are very elusive at the visual pH. So this was my last slide. I want to more than recap and jump on the future perspective of the story. From the targeting point of view, we are now working on RNA, and I hope next time I'm going to bring you some fresh news. We are using an RNA model system, a premier, rather big structure, to try to target this in cells. And for the aptamer stabilization story and the decoy story, we are testing, of course, new topologies rather than the antiparallel. And the idea now is in collaboration with Dr. Di Antonio in the Imperial College, where I'm going to move from next November. We're going to test this technology. Well, we're actually testing already this technology in cells. So I would like to thank all the collaborators of these works, especially Jack, because he helped me for doing this aptamer story recently, and also he gave his own blood for doing all the experiments, which is pretty amazing to say. And all the collaborators, and of course the funding agency, and you guys for your attention.